For decades, foundational applications relied on a strict client-server model, all incoming user requests routed to a single, centralized machine housing the database. A single machine has finite physical limits. It possesses a set amount of processing cores, memory, and storage, which caps its computational capacity. It is also bound by geographic network latency. Data takes physical time to travel through fiber optic cables, meaning users situated continents away from the server experience significant delays in response times. Most critically, relying on one machine creates an extreme operational risk. If a power supply fails or a hard drive corrupts, the entire application drops offline. Centralizing data places a hard ceiling on how many users a system can serve, and guarantees that a single hardware malfunction will result in catastrophic downtime. To bypass these hardware limits, engineers pivot from the single server model and distribute the workload across a cluster of multiple connected machines. This requires a process called replication. Replication is the physical duplication and storage of identical data across geographically distinct nodes. By routing the user requests to these distributed copies, the system operates independently of the CPU and memory constraints of any single piece of hardware. This physical distribution is the structural engine required for high availability. High availability is a system design approach that ensures an application meets a predetermined level of operational performance for a higher than normal period. However, placing the exact same data on multiple machines scattered across the globe introduces a severe logistical challenge regarding identical data states. Generating copies solves the physical hardware limits, but it forces the software to constantly synchronize the state of that data across the entire network. A replicated system is designed to achieve 3 specific operational mandates, beginning with fault tolerance. If a localized machine catches fire or loses power, the incoming network traffic immediately reroutes to the surviving nodes. The data persists because it exists independently in multiple physical locations. The second operational mandate is performance, achieved through geographic proximity. When an Indian user requests an image from a US server, data physically crosses an ocean. Placing a replica directly in India cuts that path to miles. As this chart shows, the long-distance US route takes high milliseconds, while the local Indian replica drastically reduces the delay. The third operational mandate is load balancing. Instead of blasting a single database with millions of simultaneous requests, a traffic controller distributes the incoming reads and writes equally across the entire cluster. This distribution prevents any single compute unit from bottlenecking. The response times remain stable, even during massive spikes in user activity. Combining fault tolerance, localized performance, and load balancing transforms isolated hardware into a resilient global network. When designing this network, engineers must make a core architectural choice regarding how the replica nodes interact with one another. The first structural methodology is active replication. In this model, every single node in the cluster processes every incoming request. A client sends a write command, the command duplicates, and all nodes execute the exact same complex algorithmic sequence simultaneously. This yields maximum data consistency. Because all nodes run the calculations concurrently, they arrive at the new data state together. The drawback is massive computational redundancy. The system burns CPU cycles on multiple machines just to process one basic client request. This limits the scale of the cluster. Adding 10 nodes to an active replication network does not increase the processing throughput. It just means 10 machines are executing the exact same math. Active replication guarantees a perfectly synchronized state, but wastes immense compute power to maintain it. To conserve processing power, systems often use a second architectural approach, passive or primary backup replication. This topology establishes a strict hierarchy. A central orchestrating primary node sits at the top, routing connections down to peripheral backup nodes. In this workflow, incoming client requests are routed exclusively to the primary node for execution. The primary node completes the calculation. It then takes the final updated data state and pushes that completed package down the tree to the backups. This saves processing power. The backup nodes do not calculate the math. They simply overwrite their internal files with the primary node's final answer. Relying on a single node to calculate and then transmit the answer introduces a propagation delay across the network. While passive replication operates with high compute efficiency, it opens a physical window of time where the backup nodes hold outdated, invalid information. That microsecond gap during data propagation is the critical vulnerability of distributed systems. Consider a scenario where client A changes a variable from X to Y. Node 1 updates its local status to Y and must now transmit that update across the network wire to Node 2. That data packet is bound by physical travel time. Before that update packet finishes traversing the network, secondary user client B queries Node 2 for the data. Because the update is still in transit, Node 2 serves the obsolete X data to client B. This phenomenon is known as state drift, or data inconsistency. Two users query the application simultaneously and receive conflicting facts. This is not a software bug. It is an unavoidable physical reality of storing identical data on geographically separated machines. The illusion of a single, instant global data state breaks down against the strict physical limits of network transfer speeds. This exposes the synchronization paradox. Replication is mathematically required for system survival, but it inherently fractures logical consistency. Resolving this requires dealing with synchronization overhead, the massive network bandwidth and performance cost incurred by forcing nodes to constantly verify each other's state. Systems engineers cannot eliminate the speed of light. The propagation delay is a permanent fixture of the network architecture. Since the delay cannot be removed, engineers must explicitly dictate how the application behaves during the delay. This is governed by consistency models. A consistency model is a theoretical framework that defines the exact sequence and timing rules for how data updates propagate across a distributed system. These models force engineers to choose between extremes. You can configure the system to halt all incoming requests until every node is perfectly updated, or you can allow users to occasionally see stale data to maintain high processing speeds. Determining which trade-off to make is the absolute necessary next step for architecting reliable global infrastructure. Distributed engineering requires making infinite copies of data and then implementing the rigorous architectural choreography necessary to keep those copies synchronized.